Okay. Hi, everybody. My name is Thomas Munro, and I'm going to be talking to you about parallelism in Postgres version 11 and the earlier versions leading up to that. There are a couple more people coming in, so maybe just wait a moment. No. Okay. So just a couple of quick words about myself. I've been involved in Postgres for about 3.5 years now, and recently became a committer. I haven't committed any large features yet, but look out. So I'm a member of Enterprise DB's database server development group. I'm based in New Zealand. If you follow the San Andreas Fault south from here, about 15,000 miles, you come to my house. There's a huge list of people who've been involved in working on parallelism in Postgres. It started at EDB with Robert Haas and Amit Kapila, but now a whole bunch of people from many different countries and companies have been involved. I personally worked on parallel hash joins, which Magnus mentioned in his talk just now, and I'll be covering a little bit in this talk. Okay, so if you look over the last few releases of Postgres, you can see that if you go back to 2014, 2015, 9.4 and 9.5 came out with some of the infrastructure for parallel query processing. But it wasn't really useful to end users. The background workers started to be used by various extensions to do some interesting stuff. There's some other bits that were a bit more obscure, and other people didn't really start using them until more recently, dynamic shared memory segments and so forth. But then 9.6 came out in 2016, and that actually had parallel query execution. It had parallel sequential scan and partial aggregation, and it could parallelize some kinds of queries. But it wasn't turned on yet because people were not sure about it, and we needed experience. Postgres 10 came out in 2017, and it finally had parallelism turned on by default. So who's used Postgres 10 with parallelism? Like a lot of people. So that's cool. It also added a bunch more executor nodes and partitions, which are a really big deal and closely related to parallelism. But as I say, the key thing about Postgres version 10 was that it was turned on, so suddenly all these people discovered parallelism. It just started happening automatically. They also discovered bugs, and then we fixed them. So Postgres 11 is about to come out, and it introduces a couple more executor nodes: parallel append, parallel hash join. It also introduces partition-wise joins. And another really useful feature is parallel create index. So in this talk, I'm going to go through some of these things and explain what they really mean, what they do, how they work. Okay. So before I do that, I'm just going to talk about some historical context for parallelism in databases. If you go back to 2004, Herb Sutter, a really well-known C++ guru from Microsoft, he wrote an article called "The Free Lunch is Over." It was quite influential and widely read, and I saw versions of this slide at a bunch of C++ conferences I used to go to 10, whatever years ago. Everyone was talking about this inflection point where single-threaded CPU performance stopped going up. It began to plateau. Can I reach that from here? I can't really use this pointy thing on a white screen, apparently. But you see around about the middle of the 2000s, you see that there's a distinct inflection point in single-threaded performance. But around about exactly the same time, the number of cores in typical chips started to shoot up from its historical level of 1. So the really difficult thing is how do you actually your software stops getting faster for free. So now you need to use more cores somehow. That's actually really hard in general. I mean, it can be simple in some cases, but certainly for database query execution, it's a fairly tricky problem. And actually, multiple CPU systems have existed since the 1960s, which is not that long after the invention of computers as we know them. So none of this is new, but it used to be really expensive. So 1960s, 1970s, we had Burroughs, IBM, later on Cray supercomputers and these kinds of things, and they had all kinds of arrangements of different multiple CPUs. But they cost millions of dollars, and you wouldn't run into them at a typical company unless you work at a massive bank or something like that, government or a nuclear research facility or something like that. But then in the 80s, we start seeing mini computers that have 2 CPUs in them, VAX systems and so on. I don't know much about those myself, but there's a really interesting system, the Sequent company. They produced computers called Symmetry and Balance and some others. I find them very interesting because, firstly, I understand them. They ran Unix, and I can sort of understand what they were doing. Secondly, Postgres was written on that system, among others. And thirdly, it was not too expensive and had like wild numbers of CPUs, up to 30 of them in a box. And that white thing that looks like a beer fridge, that's a Sequent, I think that's a Symmetry, but I'm not sure. So Postgres was actually developed on machines like that at Berkeley, not far from here. Those things were created by a bunch of people who left Intel and created a startup company that shoved a whole lot of Intel CPUs into a box, and they figured out all the memory addressing stuff to make that work when it wasn't that obvious or automatic. Fast forward a little bit of time into the early 90s, and the big iron Unix vendors, Sun, HPUX, these kinds of systems, started to come out at a much lower price point, and suddenly you could do multiprocessing in a relatively small business. You could have $20,000 or something like that. And then by the time you get to the end of the 90s, sub $10,000 servers from Dell or mass-produced servers that pretty much every company that's using computers would start to buy these systems, and they had multiple CPUs. They had dual or quad Pentium CPUs or whatever. And obviously now, pretty much every computer around you, including your phone, has multiple cores in it. Not that many necessarily have multiple sockets, but big servers have those as well. So multiprocessing has basically, in the last, let's say, 10, 20 years, reached ubiquity. That's what programming is now like. You've got to deal with multiple CPUs. So how does that correspond to the history of databases, in particular relational databases? Well, here's a chart showing the time in the gold color there, where the various well-known relational databases started doing parallel query execution. This is an archaeological find I made, which I found very amusing, that Postgres was both the first and the last to adopt parallel query execution. If you count the Berkeley University Postgres project running on those sequence systems I was talking about before, back around 1990 or so, they were doing parallel query execution. Then that project kind of wound down, and a bit later the open source Postgres project that we work on now, the first commit of that didn't have parallel query execution. It had been ripped out during that sort of gap there, and I don't actually know what happened in that time. I could guess that the people that worked on that all went to work at those other companies and did parallel query execution there. I don't know. That's pure speculation. And you can download the source code for Postgres 4.2, and you can see that it could do parallel query execution. It's pretty cool. Now, there was actually a system before that sort of period that did highly scalable parallel query execution, and that was the tandem non-stop system. And those systems used to run stock exchanges and banks and systems like that. But I'm not counting that as the first example of parallel query execution, because that was actually a shared nothing system, and that's a distinction I wanted to make really clearly. That I'm actually talking here about the parallelism that's inside Postgres, where you have shared memory and shared storage. That's actually quite different from the kind of parallelism that you get when you have a cluster of computers communicating. And on some level, a shared memory system, if you look at the hardware, on some level, it's all messaging, right? But the model of programming when you have shared memory is very different from the model of programming when you're explicitly sending messages between nodes. There are actually computers that you can reconfigure in software to be either multiple nodes or one single image system. But I just wanted to make that distinction between clusters of computers. Systems like Citus, MX, for example, that we saw in the keynote, and all kinds of other systems like that that actually communicate between different nodes using a fundamentally different way of distributing work. But these problems are actually overlapping in many ways, and typical systems, for example, Citus, I believe, is going to use parallelism on the individual nodes. So both kinds of parallelism happen on those types of systems. This talk, I'm talking about single node systems, shared memory, shared storage, parallelism of that kind. Okay, so let's look at a really simple example of a parallelizable problem, vote counting. So you have a whole bunch of people voting, and the votes go into ballot boxes, and then you have these people who are called scrutineers who somehow have to count the votes up. I don't know how they actually do this. This is just like an example. I'm using cartoon version of how vote counting might be done. The basic algorithm is that the scrutineers, the vote counters, they grab a ballot box and start counting the votes. And then when they're done with that, they grab another one until there are no more boxes. So we're scattering data at the level of boxes. That's the kind of granularity. And then the chief scrutineer basically waits around until everybody's run out of boxes. And when everybody's finished, the chief scrutineer can add up all the subtotals and produce the result, right? That's a pretty simple explanation for how you can parallel. And the nice thing about this is that if it's not going fast enough, you can add an extra person or double the number of people and hopefully scale the speed at which you'll complete the job linearly. Of course, there are technical factors like not enough people will fit in the room, or it becomes hard to access the boxes because people are tripping over each other, or when you add 1 million people into your room, well, it's not going to work. So there are some technical factors, but generally this is approximately scalable linearly by adding more people. So that exact example in the form of SQL might look like a select count star from a votes table. You'd probably do it with group by or something like that. That would have made the query plan a bit more confusing, so I'm just saying where party equals something. And you can see that if you run it with max parallel workers per gather equals 0, or if you run it on an earlier version of Postgres that doesn't have parallelism, you'll get a query plan like this. There's a big sequential scan over the votes table. And you can see that that query runs in just under 3 seconds, 2.8 seconds. If you turn on parallelism, or use a recent version of Postgres where that's the default, you'll see that in this particular case, it's chosen to run 2 workers. So the total number of processes that are actually running the query is 3, because there's the leader process, and then there's these 2 workers. And you'll see at the bottom there that it ran in about 1 second. So that's almost 3 times as fast. So we achieved what we wanted. We added more vote counters, and they worked together, and they all spat out a partial aggregate, which is the subtotals. And then finally, the leader process waits for them all to finish and then finalizes the aggregate. So that's what we want to see. We want to see something approaching linear scale, linear speed up as we add more workers. So that query plan shown in a more graphical way. It shows, you can see here that there's a leader process, which I've put an L below there, and then there's these 2 worker processes. You can see that there's scattering and gathering going on, and that's at the level of disk blocks. So when I was talking about vote counting with ballot boxes, that was the granularity. Here it's disk blocks. The fragment of the query plan that's below gather gets copied into these two workers. So it's running in a total of 3 different processes. So you see the scattering and the gathering, there's this kind of symmetry. So that's like a really simple example, and I'm now going to sort of dig into how that actually works under the covers. I'm going to do that by starting at the sort of system level, processes, memory, IPC, I/O, that kind of stuff, and then working up to the executor and finally the planner. So starting with the lower level, if you run HTOP or one of these type of system monitoring tools on your operating system, you'll see processes. And this is a quote from a 1989 paper from Stonebreaker, who led the Postgres project back in ancient times. They said, currently Postgres runs as 1 process for each active user. This was done as an expedient to get a system operational as quickly as possible. We plan on switching essentially to threads, to paraphrase. That was the plan in 1989, but we haven't quite got there. We're still using processes for every backend. Fast forward to now, parallel worker processes. Well, this is not quoting anyone else. This is just my words. Currently, we're still using 1 process for each parallel worker. That also is an expedient done to get a system operational as quickly as possible. That's kind of a joke. Like we might actually eventually move to threads, but right now you can see the processes just as you can with regular user backends. They show up as with a special process title saying, I'm a worker for this other process over here, and you can see the number. Those processes communicate with each other using shared memory. And traditionally, Postgres has got this big chunk of memory that it creates at startup, and then every process inherits, and then they can communicate with that through that shared memory. But for parallel query execution, extra shared memory segments were created. They're called DSM. That's like a Postgres project term. It's abstracting over the different ways of getting shared memory on different operating systems. So we created a separate piece of memory for each parallel query, and then all of the workers will attach to that and get their instructions and so on. They'll also feed their results back to the lead a process through tuple queues, which live inside this extra piece of shared memory. So in the course of getting all this parallel query stuff to work, we had to come up with a whole bunch of new primitives for coordinating work, essentially, things that can be done in shared memory that we didn't need to do before. Okay, so moving up to the executor, or executor, as some people seem to say, we had to introduce this new concept of parallel awareness. So I assume everybody here is pretty familiar with explain plans and how you have these different node types. What you see with parallel queries is you see this new word parallel that can appear before many of the executor node types. The terminology I've been using, this isn't in the manual or anywhere else, I've been using the term parallel oblivious for the nodes that are not parallel aware. I don't like to say non-parallel because they can actually appear in a non-parallel plan, but they can also appear in a parallel plan underneath the gather node, but not be aware of that. Like they're not behaving in a different way. They're simply processing a subset of the tuples because the work's been divided up in the way I was saying before. So I like to call non-parallel aware nodes parallel oblivious. They don't know if they're in a parallel plan or not. The parallel aware operators, or nodes, they do something special. They actually communicate with each other, as in when you've got the copies of the plan in different processes, the copy in each process, they're all connected together and they communicate in some way, usually to scatter tuples, in some cases to gather them. And in the future slides, I'm going to show the parallel aware executor nodes as green and the parallel oblivious ones in blue boxes. So looking at the most, I think, probably the most primitive operator that we have, and certainly a very simple one to start with, parallel sequential scan. Parallel sequential, first of all, that sounds like an oxymoron. It's like rather a contradiction in terms. But what it means is that the sequential scan, the executor node that knows how to read through a whole table, is parallel aware. It's not really trying to read in parallel per se, like in I/O terms, although that might happen if your operating system arranges for that. Really what it's about is scattering the data as it reads it, block by block, so that each process involved gets a different subset of the tuples. And it does that by using, in the case of parallel sequential scan, using a very simple shared memory counter to hand out the next block. Each time a process wants more data, it advances that block and takes that. So that corresponds to the ballot boxes in my cartoon example earlier. So that's a kind of granularity. Where we don't actually know anything about the tuples or the votes in a particular ballot box, we just know that it's somehow been divided up. The operating system view of this is that you have these three processes which are doing reads in 8 kilobyte blocks because that's the size of Postgres blocks. But the operating system, a typical operating system, will use 4K pages, so there's this page cache thing going on. But then the operating system hopefully is smart enough to detect that you're reading sequentially, even though you're doing it from different processes. The details on this vary from operating system to operating system, but hopefully what actually hits your disk is a series of much larger reads that sort of feed into the page cache of the operating system, and then our three processes manage to take the next block each time they need one. I believe this works pretty well on Linux because Linux has a read-ahead window system that has a size, I think it defaults to 128K, which works quite nicely with this algorithm. But I know that this is actually problematic on some other operating systems, so that it could be that there's some more work we need to do there. A parallel index scan is essentially the same thing. It's just that it's much more difficult to coordinate the chopping up of the scan into different blocks because each page has got a next pointer you need to wait. You can't actually advance to the next one until you've finished reading one to get the next pointer. So it's slightly more complicated, but essentially the same thing. And then parallel bitmap heap scans are similar to parallel sequential scans, but you've got a big bitmap and you're skipping ahead to the pages that contain, you've got a one-bit set, having done some kind of index scan to build the bitmap. It's essentially the same sort of thing. So I want to make the example of the vote counting just slightly more complicated, but not very much. And I want to say I only want to count votes from voters who were enrolled to vote, who should have been voting, by a very simple cartoon-like definition of that. I'm just going to say we've got a table of votes and a table of voters. So this is the simplest way to do a join, or the simplest example of a join, I think, where, and in the picture there you can see that's what they actually do at polling places, right? They sort of cross you off or whatever. Well, in my country they do in that way. So there are 3 join algorithms or join strategies used by Postgres. There's nested loop joins, hash joins, and merge joins. I'll talk about each of those 3 different join strategies and how they play into parallel queries. So a nested loop join, I've shown the nest loop join node in blue. It's parallel oblivious. It doesn't know that it's only receiving a partial set of tuples from the parallel sequential scan on the outer side, which is on the left there. Because it doesn't need to know. Each time it receives, in each process, it's going to receive some subset of the tuples from the outer side. And for each one of those tuples, it's going to go and look in the voter table to see if it can find a matching voter. And the results that it spits out will be partial results as well. And then the gather node will collect them all up. So nested loop joins actually work okay without any special support for parallelism, which is quite a nice case. And that was available from Postgres 9.6. So because all the planner had to do was just prove that, it just knows that it's okay to use a parallel oblivious join when you have a partial path on the outer side. And hopefully, I've put a picture there of a perfectly spherical cow in a vacuum, which is kind of a joke. It's like, ideally, this means you get this join operation should run in linear scalability. When you add more workers, it should scale nicely. Of course, in reality, we know that doesn't happen because you run out of disk I/O or you have other kinds of contention. But in this kind of cartoon, perfectly spherical cow world, you can then divide up the processing time over the number of workers. A key point here is that the index which we're probing, which is shown on the right there, we call that the inner side of the join. A B-tree index, for example, is already efficiently shared between backends, so that's why that works nicely. With a hash join, on the other hand, this is where you're building a hash table to probe instead of using an existing index. There are several reasons why you might do that. For example, you don't have an index, or it would be cheaper to scan sequentially than to do all the random I/O required to probe an index. So a hash join, which is parallel oblivious, it doesn't know anything at all about parallelism in this case, just the same as the nested loop join. It's going to have to finish up producing a separate copy of the hash table in each worker because it has no way to, it doesn't even know that it's in a parallel plan, right? Which is why I showed it as blue. This still produces the right result, but if you look at this down the bottom there, I showed this timeline. There's this build phase where every single process is building a copy of the hash table. Is this going to work? Here you can see that the 3, 1, 2, 3, they're all building a copy of the hash table. So by using 3 processes, we didn't make that phase any faster at all. In fact, we probably made it a bit slower because of contention, as they're all trying to read the same pages and do the same stuff and build their own copies of the hash table. So we finish up with these 3 copies here of the hash table, which is a waste of resources. Now, this actually works out really nicely if the hash table is small. So if you're joining against a very small table, but in the example we were talking about, it's this table of voters. Presumably it's very large, so that's not going to be a good plan to use. But this works, and it works. This query plan is available in Postgres 10, for example. The probing phase, once you've loaded the hash table into memory, is nicely parallelizable and divided up across the 3 workers in this case. So your total speed up from using parallelism with a parallel oblivious hash join is somewhat limited, but it's not 0. It's not a complete failure at parallelizing. What we can't do, we cannot just stick a parallel plan on the inner side, because now you would be joining between 2 completely arbitrary subsets of the tuples on both sides, and the results would be nonsense. So, if you think of the cross-referencing of votes against voters, you've grabbed a random ballot box full of votes, and then you rip out some random pages from the phone book or the list of voters. You can't cross-reference those in any way because neither of those sets is the complete set. So we can't do that. But what we can do, and this is new in Postgres 11, the thing that I worked on, is we can actually build a shared hash table in memory there, which means that the two phases of the join can now be divided over 3 workers, and then we get this ideal speed up of linear speed up with the number of workers. Of course, the reality is not quite as good as the ideal speed up, but it's still pretty good. One interesting way, I think, to think about this is to say that there's scattering and gathering going on here. There's a gather node, and parallel sequential scans and parallel index scans and so on, they match up with the gather node in this kind of obvious way. But in a kind of less obvious way, the shared hash table that's loaded into memory when you're doing a parallel hash join is a kind of gathering, right? It's bringing together. It's the opposite of scattering the tuples. So on both sides, we now have some scattering and some gathering going on. Yeah. And this particular plan is the only way that we can actually get both get parallelism truly on both sides of a join. And this could be part of a larger tree with many joins, right? Yeah, at the back.
So that table then lives in shared buffers, doesn't come out of workmem, unlike a normal hash table for a hash join, which would live in workmem?
Good question. So I will be covering memory budgeting in a moment, but I will say quickly that this shared hash table it's limited by workmem. It's not in traditional shared buffers. It's in DSM segments, basically extra bits of shared memory that we map in just for the purpose of doing that, and then we throw them away at the end. But they are limited by workmem, and I'm going to explain the implications of parallelism for workmem in a moment. Okay, so there's some other ways you can do hash joins in parallel that you can see in some other database systems. I'm not going to go into great detail due to lack of time, but there are some other systems that basically partition the data up front in order to work on different partitions within different backends. That approach may or may not be better. There's quite a lot of there's some recent academic work comparing those two approaches, but we actually do some kind of partitioning up front if we have to, because we run out of memory because of your workmem limits. But we're not trying to do that in a cache-aware way that actually makes it fast. We're just trying to do that because otherwise we can't possibly use the hash join because we haven't got enough memory because you didn't set workmem high enough or something like that. There's also the possibility of doing partition-wise joins, which I'll talk about in a moment, but that's kind of a related topic. And the third way of doing a join in Postgres and in many relational databases is a merge join. With a parallel oblivious merge join, one side of the merge join can be a parallel plan, and the other side has to be a non-parallel plan for the results to make sense. What that actually means, if it has to sort one of the sides, is bad news. It means that you have to sort the same data in every backend. So this is quite similar to the problem of hash joins. And we don't yet have a way to parallelize that that works nicely. In theory, what we should have is some kind of parallel sort that would share the work and spread it across the workers. That's not something we have right now. I'm not actually aware of anyone working on that, but hopefully someone will pop up any day now and start hacking on that problem. Okay, so and finally we have this new feature in Postgres 11, partition-wise joins, where the planner is aware of the fact that two sides of a join both have matching partition schemes, and it can convert the query into convert the join into a whole lot of separate joins and then append them, which kind of concatenates the results, right? In this case, I've got California voters and New York voters in separate partitions, and it's realized that the vote table and the votes table and the voters tables have matching state-based partitioning. That actually becomes parallelizable with the advent of parallel append, which can then run different branches of that query plan in different processes. But if you do that, then the granularity of parallelism is partitions, which is in some ways good and in some ways bad compared to block-based granularity, because it means, for example, when the last worker runs out of work to do, everyone else has had to wait for that before the query is finished, right? So whereas if you use block-based parallelism, you don't have that problem. But there are some advantages as a result of that as well. Okay, so I'm going to move straight on to talking about the planner and use. Sorry, yes, question.
Parallel append on the previous slide. Can you double parallel? Like, can you have parallel
Yes.
hash lines underneath it?
Yes, you can. You can have, in this picture I've shown here, it's got non-parallel plans underneath that, but you can have parallel append of parallel plans, yes. It gets increasingly confusing, but yes, you can. It might be that there are some reasons why you can't do block-based parallelism. For example, there are some types of scans that don't support that, and some types of indexes and so on don't support that. So that's why you can finish up with non-parallel plans underneath a parallel append. Okay, so I should add, by the way, that partition-wise join is not enabled by default in Postgres 11. Magnus mentioned earlier in his talk that that's because the planning cost is much higher, and yeah, we need to do some more. We have some more experiences with that before we turn it on, I think. Okay, so the planner, how the database decides, what strategies to use. I'm just going to do a quick recap of cost-based planning, just sort of as a setup to talk about some new topics for parallelism. First of all, when Postgres plans a query, the first thing it does is it creates a whole lot of paths, and those paths are ways that it can think of that it could possibly execute this query. And then it figures out in some abstract cost units, to the best of its ability, given various statistics and so on that it has, it figures out the cost of each of those paths. And then it picks the cheapest one of those and converts that into a plan and runs that plan. So with parallel query plans, we introduced the concept of partial paths, and those are costed just the same way as everything else in the planner, but the cost estimates are divided according to the number of workers. You may ask, well, how many workers should we use then? And that's a really interesting question. So our decision for how many parallel workers to use is not actually cost-based. You might think it should be. It certainly seems attractive, but that leads to a whole lot of circular, complicated problems in the planner at the moment, and we don't have a good answer for that. So we have a kind of rule-based system for deciding on the parallel degree. One way you can control the parallel degree is just to go and say alter table blah set parallel workers equals 42. That will, if that table is selected as the driving table, or sort of the outermost table, if you follow the outer branch all the way down a join hierarchy, that'll control the number of parallel workers. But normally, if you haven't set the parallel workers explicitly like that, it's determined by the size of the scan. And there's a GUC setting you can adjust. It defaults to 8 megabytes for table scans. It grows each time the size of the table that's going to be scanned gets 3 times bigger, we add a worker. So that's the kind of formula there you can see. So the basic idea is use more workers for really big tables. We could probably do better than that. That's a starting point. You can also control it explicitly if you find that the result with that is no good for your use case. But the number of workers that are actually used in a plan is also capped by max parallel workers per gather. That defaults to 2, which is a change in Postgres 11. So that's why when you start, Postgres 10. That's why when Postgres 10 came out, people's queries started running in parallel all of a sudden, because that GUC changed. Okay, so there's a few other GUCs that control the way parallel plans are costed. There's a setup cost. It's not actually worth doing any parallelization if the query is super small and it's just like touching one row or something like that, selecting something that's very quick to compute. So this parallel setup cost is this kind of barrier above which it becomes worth actually doing parallelism. Because parallelism involves starting processes and setting up new stuff in shared memory and communicating stuff in new ways and so on. So we don't want to do that all the time. There's also a cost for sending tuples between worker processes and the leader process, which ultimately needs to give tuples back to you, so they need to go through shared memory, and there's a cost per tuple that we charge in the costing. So both of those things discourage parallelism in cases where it's not a good idea and not going to pay off, right? Another group that's really important is workmem. Workmem has always been really important for non-parallel queries. It's actually, surprisingly perhaps, it was surprising to me when I first understood this, each executor node gets to use workmem. Mainly this is about sorting and hashing. Those are the things that use loads of memory, right? So how many sorts and hashes do you expect to have in your query plan? Well, it's probably very, very approximately related to the number of joins, something like that. So when you're thinking about how to set workmem, you've got to think about what your queries look like in those terms. And then be aware that each time a new worker is started, it gets its own workmem for each of those nodes. So the total amount of memory that can be used by a query is approximately workmem times number of processes used times very approximately the number of joins or something like that. One way to get loads and loads of joins, this is actually something to be aware of if you start playing around with partition-wise joins, is that and partitioning in general can lead to way more joins in your query plan. And therefore, you're exposed to this kind of multiplicative memory usage. So that's something to be aware of and to be quite careful with, I think. And I think we'll get more experience with that over the coming years as parallel query is more and more widely used. Other database systems have some settings they can use to completely limit memory use for the whole system and for the whole session and at the very least for the whole query. And that's something we should eventually figure out in Postgres, I think. So there are some things that you can do that will inhibit parallelism. One of them, for example, is CTEs. We actually can't scan CTEs, by which I mean with something at the start of a query. So for now, rewriting such a query with subselects can enable it to be parallelized. That's something that should be quite easy to fix, and I hope we can fix it really soon, because I know that with queries are very popular. I see them all the time, and quite often people write big data warehousey type queries using that syntax, and those are exactly the kind of things that can benefit from parallelism, and it's a shame that we can't do it as soon as they say with, right? Or we can in limited cases, but we can't push down the scan of the CTE as it's known. There's some limits on what kinds of joins we can do in parallel. Full outer joins, for example, somewhat rarely used, but that's something we don't know how to parallelize right now. Parallel hash joins in principle could support that, but right now they don't. FDWs could, in foreign data wrappers could, in theory, support parallelism really well, but there are no examples of that yet. So I think in coming months and years, people will start releasing versions of FDWs that can be parallelized in good ways. Cursors can prevent parallelism. This is a really interesting one. Max rows is something that's It's something that's in the protocol that I discovered. It took me ages to figure this out. I kept getting these complaints that people would try queries and it wouldn't use parallelism. And I found out eventually that they were using GUIs like DB Visualizer, and there's like 3 or 4 others that are quite similar, that limit the number of rows because they don't want to show more than 100 rows on the GUI or something like that. And as soon as that limit goes into that's like a hidden limit. It's in the wire protocol for Postgres. When that limit goes in there, suddenly parallelism gets completely disabled, and everyone was scratching their heads. And I actually used Wireshark or something like that to figure it out at some point. So queries that do any writing cannot be parallelized or locking rows. Another easy way to get parallelism disabled is to use functions that are not marked parallel safe. And here's one which I really wanted to get into Postgres 11 but didn't quite get it over the line, which is serializable transaction isolation. If you use that, you cannot parallelize the query, which I think is a shame. I personally really dislike cases where we force users to choose between our various cool features. It's a shame. So I'm hoping that in some Postgres release really soon now, we can get serializable with parallel. So some other future work that hopefully some people will take an interest in working on. Parallel sorting is a big one, already mentioned. Dynamic repartitioning, by which I mean taking data that is not partitioned, splitting it up into partitions based on key ranges, dynamically on the fly as you're scanning, and then perhaps joining that using a partition-wise join or something like that against partition data. So you might have on one side of a join, you might have data that's declaratively partitioned using the partition features. And on the other side of the join, you might have a table that gets dynamically repartitioned as it's scanned. That's kind of tricky. I looked into that a little bit myself. It's a somewhat difficult thing to implement. Obviously, better control of memory usage, already mentioned. More efficient use of processes and threads. Parallelizing CTEs, there's actually a commit fest item for that. I hope that manages to make it into Postgres 12. Cost-based planning of the number of workers would be really neat. It's a little bit strange the way that we choose the number of workers at the moment, and somewhat surprising sometimes. Parallel aggregation is somewhat limited at the moment. We can't take the output of aggregation and use that as the input of something else without terminating parallelism. That's kind of a bit of a long one to explain. And finally, write queries. That's like a really, really big deal. Eventually, I hope it will probably take multiple Postgres releases to get to that point where you can actually do full write queries. It means it's not necessarily a gather node. We don't ever have to bring all the data back together into one point necessarily. But that's, I would say, some way off. So that's actually the end of my talk. And I was well, first of all, let me say that obviously Postgres 11 is in beta right now, and you can go and install it with like apt-get and stuff like that. It would be really cool to get reports from anyone who wants to test it. Please write to us on the hackers mailing list or the bugs mailing list. I'm also really keen to hear from anyone who's got some either good or bad experiences with parallelism in Postgres so far. So that's pretty much it. If anyone's got any questions or feedback or anything else. Oh, also, I put a list of what I think are just a list of selected interesting blog articles written by the various hackers who've worked on different bits of parallel Postgres. You might want to check them out. That's me done. If anyone's got any questions. Peter.
You said that writes are not parallelizable. What about utility statements like create table adds?
Yes.
Are they parallelizable?
I don't actually know off the top of my head right now. Just can create table as select run? Yeah.
So that's kind of,
Yeah.
I mean, it's not in the context of pre-processing, so,
Yeah.
but I think it's a notable
Yeah.
case where you can in fact now,
Yes.
that you can parallelize create table as select.
Yeah.
Also, I think expression material views.
Yes.
These are utility statements, of course, so
Yeah.
it's one special case of writing, but I think it's important.
Yeah. Okay. Load? Yeah. There's no support for parallelizing data loading right now. That would count as parallel writes, and yeah, that would be very valuable. We don't have that.
So you mentioned like Postgres has say a base start on parallel feature. So in your opinion, what's the major gap compared to the state of the art?
Oh, major gaps between Postgres and the state of the art. Okay. Well, writing for a start is a major gap. Sorting is a major gap. Dynamic repartitioning. These are things that I've mentioned in the slides. Let's see. There's some areas related to distributed query planning that you might count as being a major gap, or you might consider that to be a separate feature set. I'm not sure. That's the things I can think of right now.
One, if you don't mind. So it occurs to me that one of the really compelling cases for single node parallelism is in the context of star schema queries. There's opportunity there to, so basically you could think about it at a high level, star schema queries as being a matter of having any local query plan that consists of, on the inner side, some scan of the fact table, on the outer side, rather, sorry, on same fact table, they're sort of independent.
Uh-huh.
So that's when if we had those bits, I feel like it would be perhaps the most compelling possible case for parallelism is stuff like that. That's more of a specialized thing, but I think that's where it might really shine. So
But if you have a gigantic scan, like in this slide here, joining against a whole ton of different indexed things, you can do that right now with loads of.
the difference is that there's multiple scans, so it's not even it's not like a query tree. It's like it's a graph.
Mm-hmm. Mm-hmm.
You're talking about where you've got a fact table with a lot of columns. Each of those columns joins to a separate table with its own index.
So it's
So
easier.
you're talking about selecting from 10 or 20 different tables
Mhm.
that are all.
There are actually different scans concurrently running against that same fact table.
Right. I see. Yeah.
They're doing probes of different indexes of
Yeah.
nested loop join. A bunch of different nested loop joins all running in parallel. So there's no contention there,
Yeah.
essentially. And that's where you get maybe the most compelling benefit of all.
Mm.
If you can work out a way of doing that, if you have a back table. So I think there's a lot of optimized smarts required there, and I feel like that's going to be in the next 3 years or so.
Mm-hmm.
We'll see.
Okay. At the back.
Your observations around tile joins,
Uh-huh.
also, like, is there now a shared hash table for hashtag as well?
There isn't. No. That would be a good thing. I mentioned on one of the slides that right now parallel aggregation terminates parallelism, because we can do this partial aggregation in each process, but then the results get kicked up above the gather node, where it all gets moved back into the leader process, where they get finally combined to produce the results. But now you've terminated parallelism. There are some cases where if we had exactly what you just said, state in shared memory that they're all contributing to, but which doesn't terminate the parallelism, that would be a good thing. It would enable many more parallel plans. Yeah.
So when we started using PostgreSQL, we disabled parallelism.
Uh-huh. Did it break?
We did it because the workmem tuning was kind of hard because we have hundreds of different types of queries, and some of them were out of memory because the workmem was too big.
Mm-hmm.
We had a bunch of selects that required a lot of memory. So we ended up disabling it because we kind of didn't know where is the kind of balance between
Yeah.
selects that don't use parallelism and the
Uh-huh.
selects that use parallelism. So we don't know because the programmer decides when to use it. I mean,
Yeah.
there are some knobs, obviously.
Yeah.
My question, I guess, is there like a PG-tune website
Mhm.
where I can plug in a bunch of numbers and say, like, this is what your workmem needs to be if you're using this amount of max parallel
Yeah.
workers per government.
Yeah, I don't have a good answer for that. It's certainly a difficult problem. I mean, personally, I think we should. I mentioned that the total amount of memory the system could use is determined by the number of nodes in the plan, but also by the number of workers and the number of queries running at the same time from different sessions. So that's a lot of stuff being multiplied together, right? We need to get rid of some of those terms, and so one way to do that I think, well, we haven't done it because it's actually somewhat difficult to make it work, but I think we should get rid of the multiplication by the number of workers. And we should say that if it runs 3 workers, then each node only gets a third of the memory or something like that. But it means the planner gets more complicated. It's something we haven't really got to the bottom of yet. And then ultimately, it would be nice if you could just say, look, here's the total amount of memory. Don't use more than that, please. And it somehow magically works, but we haven't got there yet. Yeah. Any other questions or? Okay. Well, that's me done. Thank you.